Welcome, everyone. This is, as I said, our week of EPRI Europe workshops. This is the session on offshore wind. So just a quick mention that today's session is going to be recorded, just to let you know, and we're looking forward to hearing from a great lineup of speakers. So we've got Norela Constaninescu from ENTSO-E, we've got Frank Flytkjær from Energinet, myself, Bandon Fitchett from EPRI, who's I think currently probably tucked up in bed. He's based in the US and will be online around 1 p.m. Central Time. Hannah Evans from Carbon Trust and Peter Eecen from TNO. So there's a great line of speakers with a good bit of experience and interaction. I hope that you'll get something from this. The slide deck is pretty good, so I have high hopes for the presentations. With that, I think we'll maybe get to the first presentation. So I'm going to introduce Norela. So Norela is a research manager research and innovation with the European network of TSOs for electricity, ENTSO-E. She's a member of the governing board of the ETIPS-Net and co-chair of the ETIPS-Net working group on digital and customer integration. So Norela, thanks for joining us, and please take it away.
Thank you very much, Jonathan, for the introduction. I didn't expect to start the session, but I will start it with pleasure. So yesterday I had the chance in the introductory session regarding the innovation framework, which was moderated and led by Mark McGragan, to introduce the ENTSO-E research development and innovation roadmap. And actually today for me it will be to dive in one of the flagships we identified in this roadmap. If we go to the next slide. I will start by showing the perspective of the challenge which is in front of us. So this is a slide which is developed by the colleagues in system development area. You see here what was done in terms of the 10-year network development plan regarding the scenarios, regarding the interconnections which have to be deployed, as well as the offshore wind capacity which we have to integrate. Jonathan, I apologize, it might be needed to press once again to show a little bit the numbers. Yeah, and once again. Okay, thank you. So you will see here the challenge which is expected from the offshore integration point of view. This is something which, of course, it's even more enhanced by the European Green Deal objectives. And you see the different numbers which are there. Some of them according to the Northern Sea ministers, for example, in the North Sea, but also what was brought by the European Commission through the offshore strategy, which is quite big. So it's 300, and Wind Europe 300 gigawatt by 2050, and of course something like 80 gigawatt by 2030 according to our ENTSO-E scenarios, and also Wind Europe view in this development. Of course, having all these capacities regarding the offshore wind around the North Sea, Baltic Sea, but also future developments in Atlantic and the Mediterranean. So we have to take into account the grid perspective and the integration. And the systems are going to be developed not from scratch. So of course they have to be connected to the existing systems, and hence we have started actually the discussion in ENTSO-E regarding the offshore grid development, there are multiple aspects which have to be considered. Today, I will focus on the interoperability, but in ENTSO-E, we also discussed the market issues. Is not my field of expertise, but yeah, it was. We have also a position paper on the market, and now we work also on a more general position paper regarding the integration and the system operation aspects. If we go to the next slide. Here I presented yesterday actually this ENTSO-E roadmap in order to tell you that the research and innovation activities and what we actually presented in this interoperability paper, they are aligned and very much linked. So in ENTSO-E, one of the blocks in which we look from research and innovation perspective, it's the cyber physical system, the development of the cyber physical system, and you see there the enabling of large-scale offshore wind into the grid. So now we are going to zoom into this particular area of development, and if we go to the next slide. You see here what we envisage as activities, research and innovation activities to 2030 in order to have this large-scale offshore wind integration into the grid. On one hand, of course, there are the regulatory aspects. On the other hand, are the development of HVDC technologies and materials. But today focus it's on the line in the middle, the HVDC and interoperability developments regarding to, of course, the hardware and software solutions and what is requested to arrive actually to have in the future a multi-vendor, multi-terminal HVDC full-scale demonstrator. And there are steps you see there. So some of them are building upon each other. Of course, we have the models, we have the replicas, but we need a standardization. We need also the HVDC standard modeling tools, requirements for vendors, especially related to converter capabilities to the DC connection point. And then, of course, we should move towards the definition of the pilots, and afterwards to have this multi-vendor, multi-terminal HVDC full-scale demonstrator. If we go to the next slide. So the work was actually rather intense for us. I think it's almost 1.5 years we worked on this, also exchanging with the manufacturers and also with the wind developers in this discussion, in order to break what we call the vicious circle. So on one hand, the manufacturers requiring the specifications to cover the assets capabilities and compliance with the system needs. On the other hand, the position of the TSOs, which cannot draft actually this specification for multi-terminal, multi-vendor, multi-purpose systems, due to the fact that there are conditions regarding the interoperability, and due to the limited operational experience in these technologies, especially when we have multiple vendors offering the solutions. And then, of course, the question was to arrive to the level of details which will allow to develop such a project. And hence, we started this discussion, and from here, this interoperability position paper was developed, not to mention the discussion regarding the terms itself on interoperability. And here you see a trial to get a definition, at least for the from the TSO perspective. If we go to the next slide, after having this discussion, we mentioned that actually, in order to arrive to these developments, which in the future we will allow the development probably of a type of move from radial connections today to more meshed concept, including in the offshore developments, we need to solve first the interoperability issue. And you see here that there are technical perspectives as well as the legal perspectives. In this trial, we started with research and innovation projects. Some of them were quite big. I would mention maybe 20s. Then we also went into the best path, which was closed 2-3 years ago. And the last one, which was on the pipeline of research, development, and innovation projects, was a promotion, which was particularly addressing the North Sea. Although these projects actually required an important effort, and we managed to move certain things in the direction of interoperability, in the end, the success was not fully there, because we realized that we have to start from the planning, and then to involve also to have this cooperation between the manufacturers and the TSOs in order to allow this granularity, which I mentioned before. So the technical issues which still need to be solved, so the functional and operational requirements, power system engineering and planning. So this is important. We want to have, after trying to figure out the exact location, the granularity, to arrive to this demonstration in a target environment, so a real scale demonstration, and then to have standardization of systems and equipment. Then, of course, working with the manufacturers, there are intellectual property rights which are raised by the manufacturers, contractual relationship and warranties, and the regulation and the legal framework. Of course, the TSOs need to have relevant studies around the real case. If we go to the next slide, another one. Okay, in the end, after all these discussions and putting forward the issues which we need to solve, we arrived actually to tasks which have to be fulfilled by the TSOs, by the manufacturers, and of course we need also the support of the policy makers. So I mentioned the need for actually adapting actually the planning approaches. So in order to allow this interoperability to take place, so we need to have the real case conditions, and then of course we need to have this planning in the real case condition. Then the drafting of specification on the DC side, and what I would say, the planning should be there to de-risk the future projects in the conditions of multi-terminal, multi-vendor HVDC system, the development of rules and requirements, and of course maybe the formulation of the new guidelines, then the development towards a full-scale demonstrator to reach actually the high technology readiness level, in order to facilitate the standardization of systems and equipment to allow for a plug-and-play approach. From the perspective of the manufacturers, of course, I mentioned the required level of detail and clear interface of models to be used for the interaction studies and pre-studies in the multi-vendor environment. The definition of contractual and legal relationship in order to establish the multi-vendor cooperation framework, and in the future standardization of the components and equipment when technology readiness level it's reasonable. From the policymakers, we actually push the idea that we need to have a sound legal and regulatory governance for developing such a full-scale multi-vendor, multi-terminal demonstrator. And I think in Europe, the offshore strategy recognized this need in a well-covered way. And of course, in order to arrive there, we have to take a stepwise approach and start with the relevant development and demonstration activities before going to commercial viable infrastructure. And if we go to the next slide, which I think is the last one. So all this we do to move from the today situation to tomorrow perspective, where of course we will have the hybrid projects development. When I say hybrid, means so interconnector plus the connection of the wind farm, and this idea of arriving actually in a multi-terminal, multi-purpose development in order to open up actually the development of potential meshed offshore grid for integrating those amounts of huge offshore wind developments I have shown on the first slide. So interoperability, it's important, and it's for the moment seen as an implementation risk for the TSOs, and hence we would like to move forward and have the de-risking of such a solution. Thank you for your attention.
Thank you very much, Norela. That was great. And just in case others didn't see it, Eamon put the RD&I roadmap from ENTSO-E and the position paper into the chat there, the links, so you can get those. So I guess if there's any, I see maybe one specific question for Norela, or maybe two. Maybe in the interest of time, Norela, you might address those in the chat, and we'll move on to the next presentation, and we'll come back to Q&A at the end.
Okay, fine.
Great. Thanks, Norela. So next up we have Christian from ENTSO-E. So Christian received, or sorry, not ENTSO-E, Energinet. Christian received his bachelor's, master's, and PhD from Aalborg University. He's worked with Energinet, the Danish TSO, in various roles over the last 10 years. The first 8 years as a power system specialist, and the last 2 as the head of the section. He's currently head of grid analysis, department responsible for power system studies related to planning, design and operation of the Danish power systems. And Christian is going to speak about the Danish offshore energy islands, which is a very interesting topic and one that I'm really interested to hear about. So Christian, please take it away.
Thank you, Jonathan. Good day all. I'm happy to be here. I will present on the Danish energy islands, and this is quite a well-fitted topic, both because Norela gave me the perfect introduction and because this topic is innovation. So we were given the task by the Danish government that decided we should construct these 2 energy islands approximately a couple of months ago. So you are invited into the engine room of Energinet very early in the process. So what I will present is basically a series of slides containing only questions. So a lot of innovation needs on the slides to come, and looking forward both to input and maybe cooperation in the future. So if you'd change slide, please, Jonathan. So as mentioned, the Danish government has decided as a part of the Danish green transition to construct 2 energy islands, one in the North Sea, 3 gigawatt, that has to be completed by 2033. What is special about this one is that it has to be expandable, going at least to 10 gigawatt. There will also be a smaller energy island in the Baltic Sea, and here we will utilize the island of Bornholm, you can see on your right. As a first starting point, it will be 2 gigawatt, but it has to be done in 2030. And just for those of you that are not that familiar with construction of these projects, this means that tender has to go out either the end of this year or next year. So basically all the problems Norela just described, we need to solve them within a year. So we are quite busy. Next slide, please. The whole idea of the energy island is, of course, to land wind power, but it also to interconnect countries so that we will start constructing this offshore European grid that enable us to harvest the 300 gigawatts we have in plans currently for the North Sea energy island. We are discussing with colleagues in Norway, UK, Belgium, the Netherlands, and Germany for possible interconnectors. Of course, none of this is fixed yet, as again the projects are very immature. In the project in the Baltics, we are looking for discussions with colleagues in Sweden, Germany, and Poland. And the idea is that as the islands expand, more partners could be interconnected, either by connecting different islands or directly to their respective countries. Next slide, please. So there are 3 hubs in play. If you have followed the North Sea Wind Power Hub project, which is a cooperation between TenneT and Energinet and other partners, the first pictures you saw were these sand-filled islands. Even some of them had a little lake, and there were some trees and bushes, and so this was how it started as a vision. Now it became more concrete, and over the last years, mainly the platform solution and the Eecen solution has been discussed. So if you give a go again, Jonathan. The Eecen has been chosen for the North Sea, and this will be the first artificial energy island in the world. It will be situated approximately 80-90 kilometers from the peninsula of Jutland. Again, it has to be done within 33, meaning that specification has to go out in 3 to 4 years for us to fulfill the time requirement. It's a significant investment, the largest in the history of Danish construction, 28 billion euros. This is including the 10 gigawatt wind farms, electrical installations, and power cables. A bit special about the island is that it will be a public-private partnership. I think public owned 51%, and then rest by private. So this is also a new way of doing this in Denmark. So next slide, please. The idea is that the first 3 gigawatt will be constructed as an electrical landing facility, either AC or DC current. The idea is then later either to install Power-to-X plants on the energy hub itself, or to land the energy by electricity and then transform it at onshore. So the whole Power-to-X is thought into the idea from the beginning, but the first stage will be an electrical hub only. The next slide, please. So as I mentioned, this is the vision for the European North Sea series of interconnected energy hubs. that somehow starts us developing our offshore HVDC European system. So the start of something that will be very, very interesting to follow over the next 10, 15 years. So next slide, Jonathan. The next slides, they are the innovation needs and technical challenges seen from a system operator's perspective, and especially the electrical system operator. The gas colleagues, they are also involved in the project, but this is a focus on the electrical system design. So you could say basically that this hub is an extreme version of the future inverter-based power system. So this is a unique opportunity for us to gain skills and to learn, to share experience. If we follow the time plan, which we of course intend to do, then in 23 we have both been through the planning, through the design, and we are able to actually measure the electrical performance of this island. So there's a significant learning that will help de-risk future energy offshore facilities. So this is something which is very, very interesting from an innovation point of view. What we are responsible for at Energinet is to construct the offshore power system, the landing facilities, and the interconnectors together with neighboring partners. It's of course to establish the technical and regulatory framework to support this. So next slide, please. We have divided the problems, again, seen from a system operator's perspective, into these 6 categories. We have onshore system integration, we have hub stability, we have modularity and interoperability, and here the modularity covers the need to expand, saying that we will construct 3 gigawatt first, and then in coming years we will expand again towards the 10. We also have a unique opportunity to address normal operation as we design basically this offshore power system from the beginning. So what is actually the optimum configuration? Model and data exchange, which was also touched upon by Norela, is extremely complicated. Basically, you have to tell competing partners that they have to share their most highly secret models and data to their competitors, and even if you take into account modularity, then you also have to tell them that they need to probably share it with future entities that are not named at this time. So this is very problematic to solve from a regulatory and legal perspective. Of course, there are the grid codes and connection processes. So next slide, please, Jonathan. So what we're doing now is investigate topology candidates. We are 80 kilometers offshore, meaning that an AC landing system is not out of the question, and this is what is seen at the left. What we have in the middle is an AC or DC combined landing system, and this could also be the pure DC landing facility. What we have on the right is what also Norela addressed, the multi-terminal, multi-vendor HVDC system. So we are now in the stage of evaluating from an economical and technical perspective with the boundary condition that we need to be able to expand it in the future. What is the optimum configuration we should select for these energy islands? Is it the same for both of them, or is it different? Next slide, please. You can see here already that this is these decisions on technology, AC or DC, will have huge effects on what sort of innovations and what sort of issues we need to challenge. Basically, on the left, you have single HVDC systems, and you have the connection on the AC side on the island. Here you have, of course, to control what is an AC offshore power system using some sort of hub master controller that has to be developed. Here, interoperability between HVDC systems will also be highly relevant, because you have very close interconnected components in a very weak AC system. So you have all the components for controller interactions and many of these phenomena that needs to be addressed on such a high-risk offshore system. On the right, you have moved the hub connection between the different HVDCs to the DC side, and hence you have started the multi-terminal system, because we need to expand this to 10 gigawatt and maybe also connect to future hubs. This needs to be a multi-vendor system for us, not to be locked to one vendor. So we need the multi-vendor, multi-terminal system for us to enable the right choice here on the figure. So Jennifer, next slide, please. So these are some of the questions we have specifically for the two candidates. If you take the AC hub, basically what you do here is to specify the offshore power system from the beginning. So what are normal operation conditions? This is a facility that should land wind power. So if you could somehow optimize the offshore system to facilitate that towards the wind turbines, that could maybe be a very good idea. For instance, you could, in an inverter-based system, you could have a very good control of voltage. So maybe you could limit the normal operation band of the voltage, and hence auxiliary systems in the turbines could be specified and become cheaper. Maybe you should have the voltage control on the DC systems. Maybe you should have it combined on the voltage or on the turbine and the HVDC systems. Maybe you even need auxiliary components as the synchronous condenser, and so on and so on. So many questions to answer on the operation of the hub. What is especially interesting is, of course, that this is a low system strength and no inertia system, so you have strong coupling between plants, and hence you need detailed models and data to specify it and ensure you can operate it safely. And hence you run into the RPR issues that you need to share this between vendors that are most likely in competition with each other. So how do you ensure that, and how do you ensure that you can also expand the island in the future, so that the whole set of data that you have shared between parties already on the island can be shared with a future connectee on the island, and what is the responsibility and what is the between these parties if plant number X somehow leads or motivates a problem on the island. We have the whole grid forming functionality requirements. Should it be done by HVDC? Should it be done by a combination of wind power plant and HVDC, or how should this be done? It will probably be easy for the first 2-3 gigawatts. This has already been done by colleagues in Germany. But what when you have, for instance, 10 gigawatt of wind power, of course, one HVDC of a couple of gigawatt will not be able to control such a hub. So grid forming functionalities should be seen from a system level. Of course, then there's also the influence onshore. In Denmark, we have largest unit we can lose of 700 megawatt, but the optimum seems to be a 2 gigawatt solution. So could you couple 300 megawatt of flexible consumption to the hub, so that when you lose an HVDC, you will not be able to, or you do not need to procure the last 300 megawatt in the market, and so on and so on. And also, how do you see disturbances propagate from the island to the onshore? So again, a series of very interesting questions that needs to be addressed. Next slide, please, Jonathan. So again, should we go for the HVDC solution? As Norela has already pointed out, this is a highly innovative challenge, and this is both for the regulatory framework and for the technical framework. We need the standardized interfaces, and when we talk about this is both voltage, this is signals, this is the rules and regulations, this is the legal framework, this is all these aspects that needs to be addressed before we can start constructing these HVDC blocks and basically connect them like Lego blocks to construct these offshore hubs. So especially the regulatory and the legal framework, I think, will be a very, very interesting challenge that we need to solve. Multi-country HVDC grids will be introduced as a part of this solution. So how do you control and operate the DC grid, and what sort of DC grid codes should be developed? They do not exist today. specification and development of the controller, and especially this with assessment of risk and benefit. So who should be the first to construct the first European multi-terminal, multi-vendor, multi-purpose, multi-country HVDC system? Should it be one of the Danish energy islands? These are questions that we are looking into today. So next slide, please. This is the last slide, and this is just to point out that the building blocks for answering many of these questions do actually not exist today. Of course, we have EMT models well developed, we have the RTDS, and we have all these components available. But one thing we miss in the specification stage, and because there is such it's such a rough electrical environment, probably the generic models will not do. So how do you write the specification for the tender materials for the first 3 gigawatt, and how do you do it for the next until you run up to 10? So I think there will be needs that we need to address this. So what can you do with generic models, and when do you need vendor specific models, and vendor specific models are not delivered to you until you sign the contract. So what can you do with EMT studies? What can you do with frequency domain studies? Eigenvalue-based methods, something we need to look into. Should you have the real-time simulations from the beginning? And all of this has to go into the grid code that probably takes a couple of years to change before you actually have the specification in place. So the whole toolbox for developing and answering many of these questions also needs to be addressed as a part of the innovation here. So thanks, Jonathan. Could you just change slides? So this is the last slide. So thank you for your attention.
Thank you, Christian. That was great. I think maybe we have time for a couple of questions, and there was a couple that came through in the chat. Maybe one from me first. I'm just thinking, so the design choices you talked about, especially whether you have AC interlinks or you do a DC connections between the 2 or 3 HVDC links. Is that design choice on you, or is that design choice on the developers of the offshore system?
The Energinet, as the system operator, has been given the task to design the landing facility, and the task is to design landing facility for 3 gigawatt that enables modularity until 10 gigawatt, and then within that boundary you have to find the optimum solution. So one thing that is considered, and it's pretty difficult to answer, so how much should you pay today to enable future expansion in a world that is onshore? Do you need to start with the multi-terminal, multi-vendor system simply to be able to fulfill later needs, and how should you justify this cost now when things are moving so fast, technology is developing, and a lot is going on.
Okay, thanks. So we had another question in the chat. Do you have an estimate on how the energy islands may decrease costs, risks, or project timelines for the actual offshore wind development?
Yeah, this is not my area of expertise, so I would rather not address these questions, but I have competent colleagues that are more capable.
Great. And then maybe also a little bit outside the environmental impact of an offshore wind hub, any restrictions that need to be considered.
Yeah, that would be the same answer. Again, this is from the electricity system operator's perspective, and there are many issues to tackle, environmental and technical, regulatory, and so there's a large organization working on this.
So I guess the last one for me, maybe a more difficult one. What's your top innovation that's needed in the next 5 years?
I think this is quite difficult to answer until the most optimum solution is selected. But I think one of the most challenging topic we have to address in Europe is ensuring interoperability of multi-terminal, multi-vendor HVDC systems. This is significantly challenging on all levels, procurement strategies and regulatory and legal and technical. So here all many different areas of expertise needs to come together and ensure this framework for the future. So I think this would be where I point.
Great, thank you, Christian. So I think there's maybe a few more questions in the chat that if you want to take a go at them there, and we will have time for Q&A at the end as well. So thank you, Christian, again. So I'll just move on to my own presentation. So I realized I didn't really introduce myself at the start. So I'm Jonathan Ruddy, based in Dublin, working for EPRI Europe, and I work mostly on HVDC planning, integration of offshore wind, integration of renewables in our grid operations and planning department in EPRI. And that covers a lot of the topics that Christian has been talking about in terms of the integration of offshore wind. So the last two presentations from Norela and Christian have been a really good setup for this. They really focused a lot on the offshore network and what's needed there, and those innovations are really major challenges for the industry and are really things that we need to figure out as an industry. But this topic, from my point of view, I'm going to step a little bit more onshore and talk about some of the integration challenges which we need to think about from the onshore side of things, and how we can accommodate all of this offshore wind. We're talking about gigawatts and gigawatts of offshore wind. The targets are astronomical for Europe. 300 gigawatts by 2050 of offshore wind. I think the first point that I'd like to make is that there's a lot of discussion about meshed offshore grids and HVDC grids, but that AC connections probably aren't going to go away. And for the majority of countries who are starting out on this offshore wind journey, they're going to connect very big offshore wind plants relatively close to shore with AC connections. And there may be some meshing or modular build out like we see in Belgium, but for the most part they will be point to point type of AC connections. And at the moment, those are challenging systems to design and integrate. You've got a long AC cable, potentially with reactive compensation. You potentially need reactive compensation onshore to meet the voltage requirements, the grid code requirements. You potentially need synchronous condensers, STATCOMs. Standardization will also obviously help some of this, but I think that there's, from an integration point of view, there's a lot of things that we need to understand, both from an operations and planning point of view. And some of those being, control resonance, stability, implications of long AC cables is one thing. You talk about cities at the moment having high voltage issues at night because of the amount of cabling that they already have, the amount of AC cabling that they already have, and you introduce another 80 to 90 kilometer cable in there. That's an operational challenge for the system operator that we need to address. And another aspect to that for the system operator is that the flows will change compared to what they're used to at the moment. Changing the operation of the system is a challenge to kind of overcome. Other aspects, mitigation of harmonics, control and regulation, transient voltages and protection. Protection is one aspect that is incredibly important, and I think needs to be called out a little bit more in these sort of forums. And coordinated control of parallel plants. So, designing a single or maybe two AC connected offshore wind farms is not easy, but it's much less difficult than considering the impact that 10 gigawatt, 20 gigawatt of AC connected offshore wind will have in your system. So I think there's still a lot of integration challenges in the system needed there. So another aspect to speak about, maybe just briefly, is the impact of maybe common mode failures for AC connected offshore wind farms, or even DC connected offshore wind farms. So you have an event like the Hornsea event that causes maybe multiple offshore wind farms to react in a similar way. How do we plan against that? What models do we use to define the standards for that, and how do we try and mitigate against that happening? Those are all topics that we're really interested in researching here at EPRI. DC connections, I think that's been covered a lot in the last two presentations, so I've kind of left this slide light. And I would say that, and Christian, mentioned as well, point-to-point DC connections with offshore wind farms with maybe 2-3 offshore wind farms connected together. That's pretty well understood at the moment. It's been done in Germany quite a lot. But as we start to add more parallel links, we still need to understand stability in the offshore network, 100% inverter offshore collection network, what's the impact of multiple parallel DC plants on the onshore side, interoperability on the onshore side as well as the offshore side, and trying to avoid control interactions which are possible through the system. All of this, all of these problems that may be solved or may be caused by control can also be solved by control, and it's just about having the proper foresight and proper models and proper studies to be able to appropriately model everything and try and figure out what's going to happen in the system. So there has been a huge push recently, in particularly in some really good studies, to a coordinated offshore and onshore approach, and I think that's obviously where Energinet are also headed with the offshore grids. National Grid ESO produced an offshore coordination study a couple of months ago. It was a really good study, and I think maybe some of the authors might even be on the call. So I'm not qualified to speak about it, but there's three points that I wanted to pull out or maybe 4 points that I wanted to pull out that really struck me. You can see from the figure on the right that it's they continue with the point-to-point current approach. The amount of connections that you have on the left-hand side of the figure compared to the right-hand side of the figure, where they have an integrated approach with DC and offshore coordination. But the biggest thing for me was the cost savings. So according to this analysis, if they began their integrated planning approach in 2025, the 18% cost savings for the cost of the onshore and offshore infrastructure, and that corresponded to about 6 billion. But if they waited until 2030, that reduces to 9% savings, because of the 5 years intervening that will be that there will be AC or DC connected point-to-point offshore wind plants. The environmental benefit is huge. The amount of landing points reduced by 50%. That's something I think we're going to start to hear a lot more about in the offshore wind industry over the next 10 years, is the environmental disruption of offshore cabling, whether it's offshore or the onshore landing point. And anything we can do as an industry to minimize that is going to be beneficial. And particularly then the onshore infrastructure. So I don't think anyone's under the illusion that we won't require onshore upgrades to integrate 300 gigawatts of offshore wind into the European power system by 2050. But this study showed that the integrated approach did minimize the onshore upgrade, and a lot of the cost savings were actually onshore compared to the offshore system. So in terms of getting to a meshed offshore grid, I want to speak a little bit about that. And what we have at the moment, we have parallel AC connections with an AC interlink. We have parallel DC connections, and Christian and Norela both touched on this. So the next steps, we're in maybe the rest of Europe. It's planning for hybrid interconnectors, planning for parallel connection of AC and DC, where the DC connection might be able to go to an onshore node, which is further away and helps to solve some onshore congestion issues. Bipole HVDC is an option, and the multi-terminal HVDC demonstrator which Christian alluded to there. I think a step-by-step approach for the system standardization and having interoperability and standardization on how we build out this is going to be very, very important. So going back to what the integration challenges are of offshore wind, so from a grid integration interconnection point of view, see there's lots of congestion and power flow issues on a simple power flow study, voltage control, of having multiple offshore plants controlling voltage at a point of connection, protection coordination, grid code compliance, operation limitations like the infeeds, which Christian mentioned. If a lot of countries have less than a gigawatt of maximum infeed limitation at the moment, there may have to be some flexibility around that. And then operation and planning with high inverter penetration. On the system planning side, the balancing network reinforcement is going to be a huge challenge for the industry. Restoration, take away the conventional generation, the black start and restoration is a challenge. Resource adequacy, we had a 2-hour session yesterday in this workshop on resource adequacy. Eamon Lanoy provided a very good overview of what happened in Texas and what we're doing at EPRI to talk about resource adequacy. If anyone's looking for the recording for that, we can share it. That was a really, really good session. Sector coupling, again, as Christian mentioned, is going to be very interesting and very challenging for integration of offshore wind. I'm not a markets guy, but there are obviously market challenges as well in terms of forecasting, curtailment, ramps, and regulation. So that I wanted to then, that's the challenges. I wanted to then talk a little bit about the innovations. So again, Christian mentioned a lot of those, and he mentioned that the offshore grid is an accelerated version of where the onshore grid is headed. And I think we can learn a lot from the offshore grid in terms of what happens onshore, especially with grid forming, inverters, and mitigating control interactions. There's a lot that is required there. I don't want to spend too much time on this right now because I know that people are still interacting with Padlet, so I'll just do a quick shout out for that again. So if you weren't with us at the start, we're using Padlet as a whiteboarding tool to try and get your innovations required for offshore wind on the system. You can interact with Padlet there. You can add more challenges or innovations as you wish. We'll come back to this in the Q&A session and maybe put us to some of the speakers what we've seen and what's maybe been the most popular topic compared to from the crowd that we have. So I'll take the final few minutes and just speak very quickly about what EPRI are doing in terms of the integration of renewables and R&D and what we're doing in particular in frequency inertia side of things. So ENTSO-E, I think, is on the call. It leads our renewable integration program at EPRI, and over the past few years, been developing a lot of stuff on reduced inertia guides. Addition of renewables replacing synchronous machines. How do we deal with the inertia issue? Where we have, in some ways in the offshore grid, we know we have no inertia, so at least we start with that. Where on the onshore we have some inertia, and we're still maybe holding on to that as a way to operate the system. Frequency response adequacy, frequency response tools that are needed in operations and planning. We've been developing a few of those over the past number of years. If you're interested in getting involved in some of the R&D, you can reach out to Eecen. What's the requirement for curtailed res? Do we need to curtail wind to provide frequency response? Should we do that? How do we do that? What's the market implications of doing it? And one thing we're very interested in is the resource characterization side of things, understanding what the resource looks like, trying to forecast it better. What are the ramps? What do they look like? And how can we characterize those using sensors or other means? To jump then to the grid forming topic, which has been a huge one over the past couple of years and is only going to get bigger. One thing that we've been thinking about is how to define a future inverter based on grid forming from a TSO point of view. What does it need to do based on its capability and within its equipment limits? So it's going to have to operate in a system that has synchronous machines sometimes and doesn't have synchronous machines other times. It's going to have to operate with other inverters without causing issues. It's going to have to contribute to balancing. It's going to have to contribute to voltage control. It's going to have to have robust fault right through. It's going to have to contribute to power quality. It's going to have to contribute to system stability, and all of that within the equipment limits. And these are the things that we are going to have to specify as an industry and try and work through. Those. So some ongoing relevant R&D in EPRI, and we've on the grid forming side of things, we have a really good grid forming tutorial. My colleague Deepak Ramasubramanian put together a really good and publicly available tutorial for grid forming inverters. Anyone who's based in a TSO should be interested in that. I think somebody's going to put the link to that into the chat now. We've been involved in the development of generic models for planning and for operations over the past number of years, and we've been working on stability of AC connected offshore wind plants, fast frequency response, and 100% inverter system. A lot of work recently on 100% inverter based systems, and something that we're continuing to work on, and in particular through the modeling and planning timeframes, but reaching into the operations timeframes as well. So I think there's a number of R&D projects which are of real interest in those areas, and that's just the tip of the iceberg. We're also working on restoration with renewables, protection, system integrity protection, and control center of the future, which are all relevant to integration of offshore wind. So I wanted to speak very briefly about some upcoming projects as well. So in our operations and planning, transmission operations planning department, we're working on projects in reducing grid strength and short circuit current. On the grid forming side, we've done a lot of work on that over the last couple of years. We're actively seeking collaboration on a demonstration on that side of things. So if there are people out there who are interested in working on that, whether through European projects or other means, we'd be very interested in talking about that. One aspect that I haven't seen talked about too much is network reductions for dynamic studies, how to reduce the computational burden of the system while maintaining the dynamics of the system that you're studying. We're also working HVDC integration, onshore and offshore. One interesting project that we're starting to kick off with our LCRI team, the Low Carbon Resource Initiative at EPRI, who you may have heard from yesterday, is the co-location of a lot of those electrolyzers, wind, storage, DC, AC connections. So that's something which will be of big interest, I'm sure. And again, as I mentioned, restoration from renewables. So that was a kind of a 15-minute whistle-stop tour of what EPRI are doing in the sort of grid integration of renewables and particularly offshore wind side of things. I have some conclusions that there's huge innovation still persists with onshore grid integration, and the offshore mesh networks do present challenges and opportunities for that. And by opportunities, I mean to relieve congestion onshore, to change where you might land the offshore wind, to increase the controllability, to increase the network transfer capability between regions or countries. And we're at EPRI, we're very interested in continuing to work on this. And if you do want to get involved with us, there's a number of ways to do that. From joining a working group or or getting involved in an interest group that's kind of the base level of getting involved, and maybe having 1 or 2 calls per year, or right up to getting completely involved in a collaborative R&D project or a project with us. So there's many ways to get involved, and we'd be very interested in hearing from anyone who's interested in some of the things that we've talked about over the whole week, actually. So that's about it from me. I don't know if there's. I think maybe I'll ask you again to go to Padlet. We're going to take a 5-minute break and come back with a presentation from my colleague Bandon Fitchett on EPRI's R&D in the wind generation department, and that'll be followed up by a presentation from Hannah Evans, the Carbon Trust, and Peter Eecen at TNO, and then we'll have a Q&A session to round out the session.
Welcome, everybody, and thanks a lot for being here today. Thanks for having me. I know this is a fairly grid operations and power delivery utilization type of meeting typically, but last couple of years we've been participating pretty tightly as the representatives of the generation sector here. And again, my name is Brandon. I lead the wind energy R&D research at EPRI, focused on the wind power plants, so pretty much everything inside the fence. We've been breaking down those fences, though, and breaking down the barriers a lot recently, and work very tightly with folks like Jonathan, folks like Aiden and Eecen on the grid operations and planning side, especially around the around the integration of renewables into the power grid. I'm going to take a moment after this break to look at this situation from the offshore side towards the onshore side, and we'll start on the offshore side of things. I know we've been looking a lot at the grid options, the transmission options a lot. I'm going to start here looking at a little bit about the wind turbines and a little bit about the plants themselves, with the angle of how those plants interact with the grid and how those plants will play a part in the future of the power system. So why are we talking about offshore wind? It's the first thing is a question of economics, and the offshore wind capital costs have really dropped precipitously, even up to 2016. But I mean, year over year, we're talking about nearly 10% per year annual cost decreases for offshore wind capital costs. When the capital costs decline, when these upfront costs are really the largest portion of the cost of energy, as these are declining drastically, offshore wind starts to become economical in areas where you have shallow water, good wind resource, fairly high power prices, and loads near shore, so cities near the shore. You have these 4 things. Offshore wind in a lot of the world is starting to become economical, starting to make sense. So the plot on the right you see here is the global annual projected build out of offshore wind. And you see Europe is really a powerhouse here. Through the 2030s, it's a third to 40% of the projected offshore wind build out in the world is happening in Europe. So other areas of the world, it is catching on. The U.S. is picking up pace, Asia Pacific, some areas where floating offshore wind is going to be needed, where land is highly constrained. That may start driving folks to floating offshore wind. But with this cost reduction is going to come additional build outs, and policy really could accelerate these situations even further. Similar situations are occurring onshore as well. The build outs onshore are nearly double or triple that projection for offshore in terms of new builds. And this has really led us to look at a different aspect of this energy transition. It's a transition within the transition. So there is a transition towards renewables and the whole power system as a whole, the generation assets. Part of that is economics, as I just presented. Part of it is policy driven. Sometimes there's a mix between the two, one claiming to be the other. And the transition within the transition I'm referring to really has to do with a drastic amount of renewables, which will be the source of generation in the future power system. A lot of these renewables assets and the specifications around these assets are designed around the economics aspects. And some of those are not really, historically not designed with the entire power system in mind, especially at the extremes, and I'll get into that a bit. For these reasons, where we see this energy transition, we brought together experts from around, again, the power industry, generation, wind turbine designers, grid operators and planners, and laid out an R&D needs roadmap for this power system of the future and how do renewables fit into it, with some of the questions being what is going to be needed from these renewables plants and what is the impact going to be on these plants? How do they need to be designed differently to be operating differently out in 2030, 40, and 2050? Looking at it that way, the plants that are going to be operating out in 2050 in an extremely renewables heavy grid, an extremely renewables heavy power system, those plants are being built in the next 5 years. These plants are going to be operated 20 to 30 years. So these plants are going to get built very soon. So some of these needs should be addressed in these assets very shortly here. The risk is that they're not. The risk is that historically, a lot of the renewables plants are built to produce as much power as possible whenever the resource is available. And some of them are incentivized even to do so with things like production tax credits or feed-in tariffs. Production is incentivized. It's not necessarily incentivized to produce when the power is needed. It's just incentivized to produce. So we see that changing, and that's part of the reason why we pulled together this roadmap. I'll post a link to this roadmap if somebody else doesn't do it right after my presentation, but the numbers here, I think this roadmap should be available to everybody. And I'm going to focus on a couple aspects today, mostly the increased dispatchability and grid services. Part of that is around the extremes of operation. We do work on a lot of other areas here at EPRI. We can't do all of this ourselves in this roadmap, though. We do work on in our wind R&D research program. A lot of the focus is on this second bullet in the reduced cost, both capital and operational costs. As these capital costs come down as a fraction of the cost of energy, the operational costs start to become more and more important. That will happen offshore as well. The improved lifetime energy production, of course. I think the dispatchability and grid services is around that energy production being when you want it, not necessarily just raw production whenever it's possible. And I think that's one of the biggest changes that's going to occur that will impact both the grid integration as well as the plant design and assumptions and all the financial pro formas around the design of these power plants and the build out of wind energy power plants. What are these power plants? Well, they are wind turbines. They're large arrays of wind turbines. A little bit different things about offshore right now is that they're going big. The next generation of offshore wind turbines are going to be 15 megawatts, 240 meter main rotor diameters. They're going to spin very slowly. A lot of them are direct drive generators, so they have gigantic multi-pole generators spinning very slowly, 7 or 8 RPM, generating 15 megawatts. The power, I'm going to go through really quick some specifications here in the second bullet, third bullet. These specifications, in terms of when wind turbines are designed to produce, are really haven't changed in 40 years. And I'd actually ask everybody to put something in the chat right now. I'd like you to type in the chat, what do you foresee as your most extreme situation? And this could be, you know, one time every 10 years, one day every 10 years. Do you think you're going to get 27 meters per second wind speed once every 10 or 20 years? Do you think you're going to get minus 30 degrees Celsius temperatures once every 10 years, or 40 degrees Celsius temperatures every 10 years? Some places in the U.S., you know, touch both of those extremes actually in terms of temperature ranges. I know there's other places in the world that do. It might be more common for you to get ice. So I'd like you to put one of three things in there. Do you think you're going to have high winds above this wind speed range for production, or low or high temperatures outside this temperature range, or ice precipitation, for example? That's another thing that can somewhat unexpectedly reduce the power output of wind energy. So we'll take a look at that chat as we go forward here. But this is something that needs to be planned for, and it's not, again, it's not economic typically in terms of just raw production if you're getting paid a fixed amount for production. To be able to produce energy at above, you know, 25 meters per second or outside these temperature ranges in most locations, it's just very rare. But it's not going to be permissible to be able to cut out and have zero wind energy when you're having 300, you know, gigawatts of offshore wind coming into your system. If there's a storm where the wind gets up to 26 meters a second, I doubt you're just going to be able to lose all that. And you won't lose all of it, but you know, losing big portions of this is something that needs to be either planned for or specified around. I know I've seen a lot of power system operators planning for the future of their offshore wind energy, and they are making assumptions a lot of times that these types of specifications are basically set in stone, that they need backup power for, you know, anytime the temperature is 1 degree outside this range or 1 meter per second outside this range. I just want to emphasize that these ranges are not set in stone at all. Again, they're 40 years old basically. They need another look. So this is a big part of what we want to do, and this is a very regional look as well. Looking at what are the statistics around these aspects, what are the needs around these aspects, not you know, not assuming that a lot of these operational specs are set. The challenges here are really operations at the extremes in terms of the operations of the wind turbines themselves, as well as flexible operation. I know Jonathan alluded to that. You know, there's a lot of automated operation that can happen around frequency response. That's usually a quick curtailment due to high frequency. The other option is uprating due to low frequency, and that can happen too. It's just not, you know, it's not utilized. There's a lot of things here that are not utilized that could be. So some types of flexible operation like that, as well as operations at the extremes. I just have to plug this real quick, and this is part of the cost reduction efforts mostly, but it is also looking at the grid, you know, some of the grid impacts and some of the electrical operational environment impacts on the wind turbines at sea. We are looking with DTU in Europe as a lead on this. We're involved in a project called Hyperwind, funded by the EU government partially, and the EPRI role here is looking at effects of grid events on the generator and drivetrain. I know we've seen some in the UK. Again, Jonathan alluded to some of that as well. And looking at the different responses needed from the wind farm is going to have some impact on the wind farm. Some are, let's say, beneficial to the life of the wind farm. Curtailment is typically will help extend the life of certain components, but transients will not, startups and shutdowns will not. So we're going to look at a lot of these different control regimes, of the future to better fit these plants into the power grid and see what is the impact on the machines of operating them a little bit differently than they are today, where they are operated to extract as much power as possible. So that brings up, you know, the challenge of the grid environment impact on the plants themselves. Starting to look the other way, starting to look at, you know, how the plants, you know, see the power system, how the plants feed into the power system. I think, you know, everyone here understands, you know, there's an average load profile, there's an average production profile, there's an average daily production profile from offshore wind, for example, there's gaps in a 100% renewable example with zero energy storage, for example. This is a look at something on the east coast of the U.S., but everywhere in the world will have similar gaps to where offshore wind and solar, in an average sense, actually fit together fairly well in some locations. But there's always going to be gaps here. How do you fill those gaps? I think that's the challenge. And what do you do in those extreme situations again, when you may have either zero solar or low solar and low offshore wind for a day? How long are those gaps? What do you need to plan for? So I know that's part of the planning, the resource adequacy aspects of this group. Again, looking from the offshore plant towards shore, there's numerous different scopes and parties involved in these offshore wind plants. The most simple case is the OEM, the developer, and the off-taker. Now, the off-taker in the U.S. case, it's really the OEM and the developer that are developing these plants all the way into shore. So it's really leading to this kind of individual connection from each plant to shore, just due to the parties involved. The European example, this looks more common in Europe, and I think it leads to more flexibility around how do you get that power to shore. It looks like there are potentially more opportunities for collaboration, and I think this is a big part of the reason that there are multiple offshore grid networks being discussed in Europe, and maybe more of a challenge in order to do that in some other parts of the world. The other aspect of this is that the developer does have, in both cases, the scope of the developer includes this offshore wind farm collection system. And those collection systems have started to step up in voltage. The typical onshore wind collection system might be, the range of 15 to 33 type of kilovolts. Offshore has stepped that up now to potentially about double that, to 66 kV. But the turbines are now getting, doubling in size again from the time that the offshore wind collection system stepped up in voltage. So there are numerous, again, looking from the offshore farm towards shore, numerous electrical balance of plant options to be considered here, and potentially, next steps in voltages to be considered as well. And I think the point here is really the challenge is there is a whole system optimization problem here with turbines, voltage from the turbines, voltage of these offshore collection systems, and integration of these collection systems into a transmission system, and then integration onto shore. So every variable in every one of these systems has impacts on the other. Again, from the turbine to this offshore electrical balance of plant to the transmission to shore and integration. And I don't, and that's something that I mentioned at the beginning that we are successfully doing and looking for more opportunities to do, is break down the barriers between these different groups that are designing these different aspects of the plant. Skipping back to this image, we really need to break down the barriers between these boxes on this screen in these scopes. So there's a lot of potential. Just imagining changing the operational specs of the turbines definitely requires the OEM collaboration. And changing the voltage of the collection system requires the developer and probably the off-taker to really collaborate. So looking through the collaboration opportunities, we are just at the beginning of doing that internally at EPRI, and we're working with other folks externally, like numerous people on this call. But it's going to take a lot more concerted studies around every group involved to really come out with a more optimized system here. So really appreciate your time here today. Thanks, Jonathan, for having me as a guest. Looking at these, looking at the offshore wind integration issue from a plant perspective. We continue to, looking forward to do more of these things. Let me know if you have any questions. And I'll be here in the chat for a while as well, and I appreciate the time.
Thanks, Brandon. Yeah, appreciate that. So we have about half an hour left, so I think we've got 2 10-minute presentations and then a 10-minute Q&A at the end. I think that'll see us towards the end. So first up, Hannah Evans. So Hannah works across the energy systems and offshore wind teams at the Carbon Trust. Her background includes developing licensing policy for Ofgem's offshore transmission owner regime. And she was recently involved in a promotion project exploring the development of mesh grids in the North Sea. She's currently working on 2 projects examining the value of flexibility in reaching net zero in the UK, and I think she's going to talk about those here. So Hannah.
Great, many thanks, Jonathan. I hope everyone can hear me okay, and thank you very much for the introduction. If you could just move on to the next slide, please, Jonathan. Thank you. So yeah, before I talk about sort of 2 of our ongoing projects relevant to offshore wind and flexibility, I just wanted to give a brief introduction to the Carbon Trust. For those of you who might not be familiar with this, so we were established in 2001 with the original aim of accelerating the UK's move to a low carbon economy, helping businesses in the public sector cut their carbon emissions and help drive low carbon innovation. Since then, we've expanded internationally with energy and climate change experts from over 30 different countries working across 5 continents, and you can see the location of our offices on this map here. In terms of our work in offshore wind, our main focus areas are the European, North American and East Asian markets, and we run 4 developer-led R&D programs looking at issues related to fixed bottom offshore wind, floating offshore wind, the environmental impacts and surrounding consenting, and integration of offshore wind into wider energy systems. And I'll provide a brief introduction to the first 3, but then focus mainly on our newest integrator program. So if you could move on to the next slide, please, Jonathan. Thank you. So this is just, as I said, the kind of overview of our 3 of our main offshore wind R&D programs. So these are quite well established programs that all take an industry-led approach to research and development. So we're ensuring that the projects that we commission under these programs are designed to kind of tackle real issues within the sector, particularly those faced by developers. Our Offshore Wind Accelerator, or OWA, is our kind of flagship program, which has been running for over a decade now. And that involves 8 offshore wind developers who in total account for around 75% of Europe's installed offshore capacity at the moment. And we've spent over £100 million through that programme, and several of the projects have led to the publications of guidelines for industry, so including things like cable burial depth assessment guidelines to guidelines for foundation design using suction buckets, so kind of quite a wide span of different topics tackled within that programme. Our offshore renewables JIP, or ORDIP, aims to reduce consenting and environmental risks for offshore programmes. And the partners in this programme include both offshore wind developers, but also representatives from the Crown Estate, who manage the seabed around the UK, and Marine Scotland, one of the consenting agencies in Scotland. And current projects under that programme focus on improving the ways in which the impact of offshore wind farm construction and operation can be on sea life and bird life can be measured more accurately to understand the kind of the risks associated with both of those stages within a wind farm's development. And finally, the Floating Wind JIP investigates the challenges and opportunities of developing commercial scale floating wind farms, and that currently includes 15 industry partners and has also been funded by the Scottish Government. So that's just a very brief overview of those other 3 programmes, but the one I want to focus on today is our integration programme. So Jonathan, if you could move to the next slide, please. Thank you. So our integrated programme was set up in late 2020 between the Carbon Trust and 6 offshore wind developers, EnBW, Equinor, Total, Vattenfall, RWE and Scottish Power Renewables. All 6 of these organisations are also part of other R&D programmes within the Carbon Trust's offshore wind programme, but they agreed to come together to kind of understand more about how the challenge of integrating offshore wind into the energy system will differ both between countries and also over time as the electricity generation mix and demand profiles within those countries changes. We were all conscious at the start of this programme that the total system cost of integration may increasingly affect the business model for offshore wind if more and more of those integration costs are placed at the kind of developer's door. or if there's a lack of kind of integration readiness within an offshore wind system that then kind of decreases the rate at which you can connect offshore wind to that system. On the other hand, we're also aware that there might be opportunities for offshore wind farms in amongst this kind of changing energy system through new energy markets and business models to provide green hydrogen. As Christian from Energinet noted in the presentation on the energy island, there's opportunities not only to export electricity but also hydrogen into energy systems, provide system flexibility services, or simply through an increase in electricity demand, there'd be a greater increase in demand for offshore wind as we start to electrify more of our heat and transport demand. Excuse me. So what we're looking to do in this first phase, it's quite a new programme that we've set up, is to try and develop a framework for kind of assessing at a high level the integration readiness of a particular national energy system, by examining aspects of that energy system that might affect either the cost of offshore wind or the revenue received by that offshore wind farm, or affect the rate of connection to the grid. And in the first phase of the programme, we're trying to develop that framework, and that's kind of a work in progress at the moment, and apply it to both the UK system and then also the German system. But the idea is that the framework would be something that you could then take and apply to different energy systems independently of this programme. And following on from that framework, the kind of second project that we're running in this first phase is a technology landscaping review to assess the technologies available or in development, which could enable kind of quicker and cheaper integration of offshore wind into national energy systems. And we then plan to select those technologies that we think are most suited or most applicable to integration of offshore wind within the UK and Germany, and develop a kind of R&D roadmap for them, which will inform the projects in future phases of the integrated programme. So those technologies could range from kind of battery storage, or technologies to improve kind of prediction of offshore wind output in order to provide more accuracy in terms of both their output to the grid, but also the flexibility services they might be able to provide, as well as things like electrolyzers and the kind of equipment surrounding the production of green hydrogen and the export of that to national energy systems. So that's a very quick overview of our integrator programme. There was another project I wanted to give you a quick introduction to, and happy to take additional questions in the Q&A, which is this one. Thank you, Dandon. The Flexibility in Great Britain project, and this actually I think links in quite well with Brandon's previous presentation around kind of looking to plan for kind of extreme events and understanding how the energy system needs to be ready for those kind of extreme weather events or extreme demand events, be those low or high demand, and how the electricity system or energy system as a whole copes to react to those. So this project, the Flexibility in Great Britain project, is being delivered in partnership with Imperial College London, and we're using the Integrated Whole Energy System model, or IWES model, which is a least cost optimization model, and it models both the electricity and the gas networks in Great Britain. And the project is being funded by a wide range of organisations, including DNOs, distribution network operators in the UK, and gas network representatives, energy suppliers, technology developers, as well as a couple of public sector bodies. The project that we're carrying out at the moment actually builds on research we did 5 years ago, which looked at the value of flexibility in reducing the cost of meeting what was then the 80% reduction emissions reduction target by 2050, and focused solely on the electricity system. And sort of given the move to the kind of stronger net zero target, and also given improvements in modelling capability, which now allow us to look across both the electricity and gas systems, we wanted to kind of revisit this piece of research and kind of update it and understand a bit more about how particularly those networks could provide flexibility to each other, and what more value flexibility could provide given that kind of stronger emissions target. And the way we've approached this research is by looking at 3 different extreme heating decarbonisation pathways. So one looking at predominantly electrifying heat demand, one looking at providing heating demand through hydrogen boilers, and one looking at installing hybrid heat pumps. So that would be a heat pump with a very small kind of natural gas backup boiler for those extreme demand periods. And then looking across those 3 heat decarbonisation pathways at the cost of meeting net zero with and without additional flexibility technologies, be those electrolyzers, thermal energy storage, battery energy storage, demand side response, and vehicle to grid storage, vehicle to grid services. Sorry. So the modelling actually takes into account the need to meet system flexibility and adequacy requirements over the course of a year, and the annual demand profile includes a 72-hour period of high winter demand coupled with low availability of wind generation to kind of understand the system requirement for backup generation and the extent to which flexibility within the system can reduce that requirement to have large kind of capacity of backup generation available for just those very short periods of the year when it's needed. I'm afraid, in terms of results, I can't kind of go into a huge amount of detail because they haven't been published yet. But we have seen across the scenarios that we've run that the one of the impacts of adding additional flexibility to the system is that it allows additional integration of renewables by making a greater use of the kind of a greater proportion of their renewable output is made use of through the use of flexibility. And what we'll have as another kind of output from the modelling is an indication of the levels of deployment of different types of flexibility technologies needed in 2050. And so to sit alongside the modelling outputs, we're also looking at doing more qualitative research to understand the kind of trajectories that we're on at the moment in terms of deployment of those technologies and the barriers to deployment within Great Britain. And so in terms of the kind of timings for this project, we're looking to wrap this up over the next couple of months and publish the reports in May. And I'm conscious of time, so I'll hand straight back to Jonathan for the next presentation.
Thanks, Hannah. I appreciate that. Very interesting. If there's any questions for Hannah, please put them in the chat, and we'll have a bit of discussion afterwards. I'd like to hand over to Peter Eecen here. So Peter, thanks for joining us. He's the R&D manager at TNO and determines the wind research strategy for a group of 55 researchers in offshore wind energy. For 10 years, he's been responsible for the offshore wind research program, which aims to accelerate the implementation of offshore wind by reducing costs and taking away barriers while supporting the Dutch and European industry to become more competitive. He is internationally active in the ERA, IEA, MEASnet, EastEP Wind and European projects, coordinator of the ERA Joint Programme on Wind Energy, which is a collaboration of 53 of the largest research groups on wind energy in Europe. And he supports industry by having a seat on the European technology platform in EastEP Wind. So it's an impressive bio, Peter, please.
So thank you very much for the introduction. So indeed, my name is Peter Eecen, working at TNO as research manager, but also the coordinator of the ERA Joint Programme Wind. And if we go to the next slide, then ERA, just a very short, is a collaboration of the independent research institutes and research groups in Europe. So we are more than 250 organizations representing more than 50,000 researchers over 30 countries. And we, on the right side of the slide, you can see that it is in all the different fields. And if you go to the next slide, that shows the Joint Programme Wind, which started in 2009 with the 13 largest research groups, and we have now increased the number of groups that participate in this collaboration to 54. And we can say that we are the leading research alliance in Europe in terms of wind energy. Next slide. And just when the slides are shared, you can find the links to the different links I included. So for Europe, I think this was included before, including the UK. You have to say nowadays we have a target of about 450 gigawatts offshore wind in 2050. That will be partly floating and partly bottom fixed, and that will not come by itself. And you can also not imagine that this enormous amount will be with the same technology as we have today. So there's a lot of developments required. And if you click one more, and the research is in different fields. And so this really requires a mature research and innovation system with higher till research and innovation that is together with performance on low till research innovation, and that shapes a research community that really can support the European industry. And maybe you know, but Europe is the #1 in wind energy at the moment worldwide, and we really want to remain that position, and the home market will be huge. So next slide. I included these slides, but I'm afraid it has a little bit too much information. But if you just take it, so we aim still for cost reductions. And the cost reductions are mainly achieved by large wind farm clusters, especially offshore. Large clusters with huge turbines, so turbine size increases, and we capture then wind conditions at larger altitudes. And that is a main driver for the cost reduction. And what we also see is that we need to improve the business case of these wind farms. You build a wind farm now, all the costs are now, but you need to know that you have a business case for the next 20, 30 years. So you want to know, can you still sell your power in 20, 30 years time when there's much more wind in the market, still at a reasonable price in order to earn your wind farm investment back. And if we go to the next slide, then the next question, of course, is also the system integration. We have been talking about that today a lot. And for example, one of the questions came up, is it bad when a wind farm disconnects when the wind speed is increasing above 25 meters per second? It used to be an economic question. It is possible to operate wind turbines even with higher wind, but it comes at a cost. So at what moment in time are you going to solve this issue? Is that being solved when you use, for example, energy islands? From the first speaker, where multiple wind farms are connected that probably are not disconnected all at the same time, and would that be damping enough to satisfy the system? So you see that there is, following the previous speakers, a sort of systematic approach to the energy system that needs to be tackled, and it impacts not only the wind turbine design, the wind farm design, but also the offshore energy infrastructure. And I call it energy infrastructure because it is not only the electricity infrastructure, it's also hydrogen or other carriers for the energy. And then, of course, we can expect maybe some breakthrough technologies, and that is, of course, the exciting part of the research, lower TRL. And there are some interesting candidates, but there is not yet a candidate which business case is much better than our standard horizontal axis 3-bladed offshore wind turbine, which tend to be larger and larger. But we keep exploring what the opportunities are. Next slide, please. Next slide. For the sake of time, I will skip this one. From the ERA perspective, and we collaborate quite a lot with it's called ETIP, it's the industry platform in Europe, and the European Academy of Wind Energy. And we see that at the moment there's a lot of focus on higher TRL, almost demonstration research. And in order to remain number one in technology in Europe, we also need to have this broad range of TRL ranges. And we are pushing the Lighthouse Initiative, let's call it. Next slide. And SETWInd, you can see as well, that is the SET Plan Implementation Working Group Offshore Wind, which is consists of countries that try to collaborate with their national programs in a collaborative way to strengthen the European research arena. So what is a Lighthouse Initiative? It's relatively low TRL, long-term and large, inclusive for a lot of different partners over a lot of countries. So in that sense, it is broader than a project, and it should help to further improve the technology readiness level of the technologies that we require in order to shape this 450 gigawatts offshore wind sector. Next slide. And the offshore wind will be the cornerstone of the European energy system. I don't know if you have seen the picture. I did not include them, but for the Netherlands, it will be certainly the largest amount of wind of power in the future energy system. In Europe, it will be a very large, but not the largest amount to the energy system. Next slide. And we have identified 3 areas where we see that a lighthouse project should be created. So the first one is to understand the physics of the atmospheric flow for wind power plant operation. And especially when you build a lot of wind farms next to each other on the North Sea or the other seas in Europe, what is the impact on the wind conditions, so the production, but also on weather and other impact. The second is, of course, enable a reliable power system operating with large-scale offshore wind, so the system integration. We heard a lot about that in previous question. And also that is the floating wind needs to become more cost effective or cost competitive. What we see is that the bottom fixed offshore wind power plants compete very well with onshore power systems. Floating is still at a, let's say, a less mature level and needs to be developed for certain areas where you have much deeper water, where bottom fixed turbines, typically up to 50 meters, I would say, is not feasible anymore. And you have to think about around Spain, at the coast, France or Portugal, also around the UK, Norway especially. So that are areas where there's a huge wind potential with relatively high, large depths. So you require floating wind. So next slide, and I can wrap it up more or less. So we have made an initiative for 3 lighthouse initiatives, and that provides great opportunities for the industry, for employment, for the innovation system to remain our #1 technology leadership in the world as Europe. And what we express is that we need an innovation system that has both low, medium and higher TRL research. You can find it in these 3 R&I strategies. So the first one is from the ERA Joint Program Wind, so the research institutes and groups in Europe. The second is from the European Academy of Wind Energy, which is mostly the universities, long-term research objectives. That is the second one. And the last one is the EPRI Strategic and Research Innovation Agenda, focusing, of course, a bit more on higher TRL, shorter term research objectives. And if you just look at those 3 documents, it provides you with a good glance of what the most urgent topics in wind energy are for the next year. And if you go to the next slide, I can conclude that from ERA, so that's the 54 largest research groups in Europe on wind energy, together with the industry platform and with the set plan implementation group, we aim to ensure a focused funding for wind R&D from low TRL to high TRL. And I do not think that we can stress it enough that is important to remain #1 in Europe in wind energy. That concludes my presentation. Thanks.
Thanks for that, Peter. That was great. And apologies if you were a little short on time there, but it was very informative. If there's any questions for Peter, let's say you get them in the chat, or you can come off mute and ask. Just put your hand up and we'll find you. Peter, one from me maybe. So and maybe after you respond, some of the other presenters might want to come in on it. How do we, we have such accelerated targets. How do we kind of balance the need for new innovations and focusing on those, and the need for just getting things built and getting them integrated quickly?
Yeah, so you're right, we need to have a balance. If we just focus on implementation, we build a lot of wind power and maybe not at the lowest cost. So in order to reduce costs and to make it more efficient, and you have presented yourself that thinking how are we shaping the energy system, the infrastructure, really makes a lot of sense in terms of cost effectiveness, but also in speed. What I, for example, did not hear from you is that if you build offshore infrastructure, the timelines are much faster than when you would like to do that onshore. The times you require to build power lines onshore is so much longer because of the inclusiveness of the population itself, that building offshore wind farms and the infrastructure is really much faster, which fits much better with the climate goals that we currently have. So it is a balance. We need the energy transition now because of climate change. On the other hand, you would like to do it at more or less optimal conditions with best technologies and be prepared for the technologies that we will implement from 2030 to 2040 and even from 2040 to 2050.
Thanks, Peter. I wonder maybe if some of the other speakers want to come in on that from their perspective, from the TSO side or from the developer side, Hannah.
If I may say something, so it was very interesting indeed to hear these different perspectives. Indeed, I agree with Peter. So, of course, the offshore developments maybe are less time consuming, especially from permit point of view. I think we face this in the TSO community, but also the wind developers as well. They started to face these constraints. What I found interesting, it's on one hand, the speed to which we have to achieve this energy transition, and on the other hand, to look at how actually we do these developments and integration in such a way that we have less impact as well on the environment. So I liked the perspective you mentioned, Jonathan, so the costs, but also the impact on the environment in your presentation, as well as what I think Bandon showed in terms of how to operate the wind farms. So not only based on potentially the production of wind, but to offer the services. And I think in the beginning of the discussion, we mentioned this impact on the environment, on the maritime place. So how many assets we put there? I think these developments have to take into account also another round of thinking on the impact from circular economy perspective.
Yeah, for sure.
Maybe a point from my view is that if we construct offshore energy systems, this typically leads to onshore infrastructure investments. So the development of the sector coupling industry will be very interesting to follow. Can we place the plants in the right location to limit grid infrastructure to speed up total construction time? And will that be possible? Will the land be cheap there? What is the business case for the P2X plants? Why should they situate themselves in the locations where we need them in terms of reducing grid infrastructure? So the whole energy system as a whole needs to address this.
Thanks, Christian.
If I can just add a point, I think there's often a kind of it's seen that kind of it's either you either focus on innovation or implementation, and that kind of one would slow down the other. But I think actually innovation would actually speed up the rate of implementation over the longer term. And I think one of the things we're coming across in the UK at least is that there's a real focus on driving down the cost of implementation now within kind of wind farms that are being built out within the next few years, that then kind of limits their ability to implement kind of like one or two kind of innovations within a small kind of subset of that wind farm that would actually then benefit future wind farms. So I think it's kind of trying to do innovation and implementation at the same time and allowing that space for innovation within the kind of near-term deployment of offshore wind farms in order to kind of speed up the overall time frame of kind of reaching our 2050 targets.
Yeah, it's a great point, Hannah. Thanks. Did someone want to follow on there? Christian?
Maybe there's also, we need to have an acceptance that, of course, the first developments will be more expensive. In my time with Energinet over the last 10 years, wind energy has reduced to 1/3. So probably when we construct our first energy island, it will be more expensive than when we build the 5th in Europe and then get started and do the innovations through the projects that drives this, and then price will reduce over time. So who goes first is the question.
Exactly. So we've reached the top of the hour, and I feel like the discussion's just getting started. I feel like we could be here for another hour, but I don't think that. I think we've asked enough of your time. I would like to thank the speakers that came and provided their input over the past 2 hours. I think it's been a really excellent session, and I think that we're really, these sort of sessions really help to shape the industry and shape what we're working on as an industry over the coming months and years, and they're great for everyone to really get their head around what the issues are and what the innovation challenges are. I really again like to thank the 4 external speakers and Bandon from EPRI for coming along. We will share the recording, we'll share the slides, and thank you everyone for interaction on Padlet as well. A few things that came up there where, you know, standardization came up a lot, and I think that goes back to Norela's initial talk about interoperability and standardization standard for HVDC, and those are very important topics to push forward for the industry. So with that, we'll leave the chat open if there's any questions. But I'd like to thank everyone for their time, and have a good day.